Let's dive in. It is November 1st. Calvin, we're sorry that you're not with us today.
Yeah,
we hope that...
We love you.
Does anyone know if he's not traveling, is he?
I don't think so.
Okay, well, if you are sick, hopefully you get back with us soon. So yesterday we ended, well, not that we ended. We were looking at this problem, and we solved what it asked us to solve, but then we were struggling. We're like, man, how could I figure out any of the other angles? Because if the angle was from the center, then it would be the same as the arc that it intercepts. If it's from one of the edge points, like on the circle, it's half of the arc that it intercepts. But what about when it doesn't do either? It's just from some random spot in the middle of the circle, and that's where we're going to head today and look at how do we solve problems and circles and information inside of those circles when we don't have them from the center or from the exterior. So just like that problem that we were looking at, Theorem 88 right here. If you have two lines going across your circle, two chords, and they intersect, we know that this angle right, oh jeez. It's okay in the lesser math classes, but when we get up here and we're trying to draw stuff, my calibration is somewhat important. So we know based off vertical angles that this angle will be congruent with this angle. So we know that they're going to be equal. The nice thing that we have now is this formula right here that if I was you, I would highlight or circle or rewrite somewhere because it might be a little blurry thanks to the copier. Those interior angles will be half of the sum of the intercepted arcs. So if we're looking for these angles, it would be either of them will be half the sum. Or you can think that together they are the sum of the arcs and then just divide by 2 to figure out each angle. Then if we were looking for these angles, it'd be the same way except we'd use the other arcs. We'd use this arc out here and this arc out there. But again, they're vertical. We know they're going to be the same. Each of them will be half of the sum of the intercepted arcs. Questions on that? Yeah. That's not a question on that, but yes. And that was more of like a statement. Sure. You did have nice upward inflection though. Sharpener? Like, yeah, am I sharper today? So now, this is where I think it's really cool. When we have two lines that are not tangent, or one line that's tangent and one line that isn't, or two lines that are both tangent, so really any way that we have lines coming from a point outside the circle, the measure of the angle made between those two lines will be half of the difference between the intercepted arcs. So, if, and this is the one that throws people off most often, if I'm talking about one where we have both lines going through and neither are tangent, we're talking about this arc out here, and then this arc right in here. Take the difference between them, divide by 2, and you have your angle measure. The other ones are a little bit easier to see which arc is which. And then this obviously will be the sum of the entire circle since they're both tangents. So if we know one of the arcs, we can figure out the other because it will be 360 minus the first arc that we know. Any questions about Theorem 89? Then this gets really cool. Kind of like cross multiplication in a way. But if we have portions of chords, so two chords that intersect each other, so I break this up into A, B, and then C, D. The product of your sections, or sorry, I should not use sections, the product of the pieces of your chord will be equal to the other product of your pieces of your chord. So, whatever A times B is, that'll be equal to your C times D. no matter what. If my point is outside the circle and the lines go into the circle, and it, like, I don't know how clear it came out on your guys' papers or if you need to rewrite this, but that now, and this is a little weird, the segment outside the circle gets distributed to the sum of both parts. So this is W times W plus X equal to Y times Y plus Z. And I like to do the distribution value first, like as a coefficient to my parentheses. So we're going to see some examples. Just hang. It makes more sense once we look at numbers. Right now we're just setting up, like, here's the rules to refer back to. Like, come back here when you're doing your practice, whatever else, like, use your notes. These are your rules to come back to. Then if I have one line tangent, and this goes back to kind of involving some of my tangent rules, I know that segment T, and then if I made another segment like this way, those would be congruent, because I know that from a point, two tangent lines will be congruent to each other. But if I have only one tangent, and then I have sections Y and Z, again, the portion on the outside distributes to the sum, and that's equal to the tangent line squared. So my tangent line squared will equal the Y times Y plus Z. Yeah? Can we have to remember these? No, once we start to apply them, you probably will. Like, they're all fairly similar, and you'll see how similar they are once we start to apply them. Probably won't make you memorize them. Like, I would give you a formula sheet or something like that. But yeah, I think you probably will end up remembering them. By the way, at the end of class, remind me that we need to talk about when you guys want to take your tests. Because honestly, I don't really care. I'd rather it be when you guys prefer. I do have to be out at the end of next week, so we'll talk about that in a second. Let's just get through our lesson. So, looking at problem 1, I went ahead and did the setup for you. I know that either of those angles will be half of the sum of the intersected arcs. So I sum my intersected arcs. I have half of, this turns into 90 plus 46 is? 136. And half of 136, my angles will be? 78 degrees. No. Ooh, not 78. Ooh, hold on.
Oh, that's
68. Yeah, 110 off. Good catch. It was before the capture, too. So try B. Now we have to use one of our different rules. We use the rule that our angle, because this is not the segment work yet, we're doing all the angle work first. The angle is going to be equal to half the difference between the arcs. So now if I don't know that arc, and sometimes also they'll connect it like this, and then they'll ask you to solve for this angle. And to solve for that angle, you first would need to solve for this arc, because you can't solve for this angle, really. So we would just start by solving that, but we'll get to problems like that. So I would first here, what do you think the best option is, especially since we have half distributed into 95? What can I do with a half on this side to get rid of it, aside from distributing? Traveler? Multiply by 2. So if I double both sides, I get 40 equal to 95 minus Z.
correct. And then you subtract 95 or add Z.
Wait, what?
Wait, you just put a times 2 on that side. You didn't do anything. Oh, wait, no, I mean,
The half.
my bad.
Yeah, that was just to get rid of the half.
Okay, I'm ready.
And then you can add Z or subtract 95.
Yeah, so I can either add Z and then subtract 40 from both sides. This is one of those moments where I would probably not say this to an average 7th grade class or an average 8th grade class. But one trick that you can start to remember is if I want to essentially get the z by itself and it's with something, and I need to get the 40 connected with the other constant, these guys can switch places. And mathematically, why that can happen is if I add z, that disappears and comes over here. Then if I subtract 40, that disappears and comes out there. So they literally just trade places as long as you leave this minus there. So this can become z equals 90. My brain's getting ahead of itself. 95 minus 40, and that is 55. And then it had asked me to solve for this angle. Let's say that's, might as well just say x. And then x would be half of that intersected angle. So that would be 27.5. Just trying to prep you guys for any of those things. So try the got it. Still uses a corollary to theorem 88. We've got a point exterior of the circle. Both lines appear to be tangent, so we can assume they're tangent. Calvin's not here, so Emma, this is going to be coming to you. The question is to have your work written down so we know the setup here. Most of my formulas, my rules relate back to the angle will equal. So Emma, here with my tangent lines, what is that angle going to be equal to? I just want like the formula set up in a way. The angle of the exterior tangent point equals what? Yeah, half of the difference between the arcs. So it's going to be half of W minus 110. Yeah.
Well, I mean, doesn't it have to really use the formula to figure out, like, I mean, the entire circle is 360 degrees, minus 110, 250.
This, if I know both these points are tangent, well, I guess that would really be like there. It's the whole circle. We know the whole arc measure has to be 360, so this has to be 250. But let's back it up with some justification. If I double both sides here, I get 140 equals W minus 110. If I add 110 to both sides, W equals 250. And my proof works out. Any questions on either way that we did that? So what you would normally see on like the practice work is it wouldn't tell you W and it wouldn't tell you the 70, or it would tell you the 70 and wouldn't tell you either of these, and then you'd have to, well, you'd have to know something. But yeah, it gives us more information than we actually need here. So, because of how I had to order my things, we're going to come back to this after problem 2. So this is like real close to actual data. So a satellite in a geostationary orbit, which is actually really cool, some of the stuff that they're talking about, if you follow anything that Tesla is doing, or like that company, or Elon Musk specifically, they're talking about having people like live up in space, just like on a space station, and then like go drop off and do things at planets and come back, and like there's really cool stuff in the works. Like you could sign up to go live in space. Like this is like in your lifetime. In your lifetime, this stuff is like happening. So like, which really like is hopefully in my lifetime, I'd like to see a colonization on Mars. I don't know if we'll actually get that far. So we are in stationary orbit, but pretty darn far away from the Earth. To see both sides of the Earth, the lens has to be open to an angle of 17.5 degrees. So, what is the measure of the arc of the Earth that it is viewed from the satellite? So like Google Maps and these sort of companies use these different algorithms for where do I want my satellite to be, how much of the Earth should it be able to see at one time. So we want to figure out how much of the Earth, how big is that arc, which it's probably not drawn to scale. Like, don't ever trust anything involving space, probably not drawn to scale. Most maps of space that you've seen are wrong. So just know that right now. Like, space scale is always screwed up. So, how are we going to figure this out? What do you think, Brian?
Wouldn't this be 108? No, are we doing the measure of the what?
We're doing the arc, so the viewing angle is 17.5 degrees. What's the measure of the arc of the Earth that's viewed?
Oh, never mind.
I'm just waiting for somebody to have a breakthrough. So if I name, I'm just going to start to like provide some names. If I make my big arc, so we're going to say AEB X, and I make my minor arc Z, then we know that the 17.5 will be equal to half the difference of X minus Z. Now we just know that based off a formula. I don't know how much that's really going to help us, but that at least gets us something down. A system of equations. If these lines are both tangent, then x plus z has to be the entire 360, which is what I meant on the front. Like, that problem gave us too much info. This is more like the type of problem that you would be solving practically. You don't know anything except for the viewing angle. So now, what can I do with this system? Like, we know, okay, I could solve a system of equations by graphing or all those different skills that we practiced last year. What do I want to do here? Easiest way. Brian?
This is what I was doing the other time. Well, Z would be 180 because the change from one edge to the other. And that's...
How is Z 180?
Because the thing.
Just because it looks like half doesn't mean
No, because it says it has to look from above the equator.
Above, so the equator would be going this way.
Yeah. Oh.
So above the equator. So that does not really have anything to do with whether it's 180 degrees or not.
Never mind.
I apologize, but it is not. If that was 180 degrees, that satellite would be pretty sweet. Like, to be able to see that much of the Earth at one given time. And then, if it was 180 degrees, the difference between the arcs would be 0. So then, half of the difference between the arcs, half of 0 would be 0. This angle would be 0. Yeah. So, using this system, I can solve for either the x or the z. So, it doesn't really matter. Let's just solve for x because it's written first. So, that'd be 360 minus the z. Now, I can rewrite my equation, but I'm going to go ahead and get rid of this 1/2 by doubling both sides. So, double of 17.5, 35. So, we get 35 equal. Now, I replace my x with 360 minus z minus z. Now you know where we're going. So now this right side becomes 360 minus 2z. And again, if you can remember why it happens, the object being subtracted, and the other side can just trade places. So we can now make this 2z equals 360 minus the 35. So 2z is really 325, which makes z Oh, come on. Just break it apart. Do 300, cut it in half. Do 25, cut it in half. Let me guess. You got 162.5. So, we're close to seeing the entire half of the Earth, but not quite there. So this arc would be 162.5, and of course x would be its buddy that sums to 360.
Would it be possible to solve for like the separate? So like, you said arc X is just A, E, B. Would it be possible to solve for the individual sections, or would we need more information?
We would need at least one other piece of information. Something. So, like, if we knew if we knew a connecting piece, or if we knew, like, a radii, or, like, we'd need to know. So, actually, with a problem like this, we could look up the Earth's radius and then use that to then solve more of this, because it's in reference to the Earth.
What is the Earth radius?
We had it in one of our problems, the one involving the CN tower.
A lot of miles.
It's like,
3,000.
yeah, I want to say it's over
Maybe
3,000 miles or something.
No,
If you go back in your notes just a few days to where we had the CN tower, it was the notes about tangent lines, I believe. Or maybe it was the trig notes. It might have been,
Yeah, no, it's miles.
Yeah, I mean,
it's miles, yeah.
No, it's miles.
So, now, try this, got it. I want you guys, especially Brian,
What did you?
try this on your own.
Oh.
It is not 180. So, we're above the equator. When it says two tangents to the equator, that means they hit the Earth at, like, the same location. Like, not that they're hitting at 180, but that they hit... Because you could hit the equator at, like, 1 degree.
Yeah.
So, we have the Earth. That's a bad Earth. We'll make it green. This is really hard. Okay, so I put the Earth on its side and make the equator like this. Then this will be easier to draw.
Wait, what does it mean by arc? Does it just mean? Oh. So does it have to be drawn vertically?
No, but this just makes sense in my head.
And can we assume the equator goes straight down the middle, or?
So I'm still drawing this poorly. If this circle, the edge of our Earth, if this circle is your equator, which I can't draw circles from that angle, if this circle is the equator, that's what it's talking about. So imagine, like, if you're looking at the Earth, like how we normally look at it, and the equator's like this, our tangent lines are going here and going there. So we want to know how much of this arc.
I think like if we were trying to draw it and then find the okay.
It's all perspective is what screws this up, because there's no perspective in space. There's no up and down. Yeah.
I have it this time.
You have it this time. Good. Let's save yourself. So, how'd you do this? Tell me like what you labeled
Well,
things as.
So, I would do the. Oh, I just did the one closest to the 20 as
Okay.
a 60. The other thing.
Okay.
Yeah,
This
Yeah.
is what?
That'd be X.
X,
X.
and then your major arc.
That's Z.
So then you set up.
And I just did 40 equals.
So he skipped a step. Be careful here. 40 equals what?
Parentheses 360 minus X minus X.
You skipped like 3 steps.
Maybe. Alright. And then equals 7.757. I do know that.
So he started with 20 equaling half the difference, Z minus X. Then he said, well, I can replace, what'd you replace? Your Z. So you said Z can actually be 360 minus X. Because they are partners. I wish, we need a formal name. Because we have supplementary, we have complementary. We don't have sum to 360. We need a formal name for that. Double. So he plugged that in. We got to our 360 minus 2x. These can flip places. What'd you get in the end? 160? Because this comes out 320. Any questions on Brian's excellent solution? Now, it scares me that you skip so many steps, so make sure that you know how to set it up from the get-go, because I would be scared if you don't do this for a couple days and you try to come back to it and skip all the way down to there. I would start back up a little higher in the process. Now, of course, those are just, I can't make you do anything, so it's all up to you. So now we get into those cool, funky relationships. Is that a hand you use stretching? Okay, just making sure. So this one I've set up for you, and actually the first one I set up for you because really, like, on your homework is the practice, like, hey, do this on your own. I know these problems are difficult. This is why a lot of times we just kind of are making examples in class. So the sum gets multiplied by the portion on the exterior. So some of these problems will give you the entire length, and then the inside length, and you'll have to solve the difference. So some of them have a little bit tricky setup. 6 plus 8. 6 plus 8. 14 times 6 is 84. 60 plus 24. Now we have an unknown. When I distribute here, what do I get?
49.
We have 49 plus 7y. So the 7 goes to the 7, and the 7 goes to the y. So check that you distributed that correctly. I then can take my 49 away from both sides. So I can just say, all right, minus 49 will equal my 7y. 84 minus 49? Well, if it was 84 minus 50, it'd be 34, so it's actually 35. What would y be? 5. So this section has to be 5. Here, all we really have to do is solve for a square root. So 8 plus 16 gives me 24 times 8. Break it up. 8 times 20 gives me 160. 8 times 4 gives me 32. 192 equals z squared. Is that a perfect square? No. So what's it come out to? Closest. Let's go decimal.
13.856.
So 13.9 if we round to the tenths. It doesn't tell us where to round, so. Oh, you're fine. What's up? Okay. Try that got it on your own. There aren't any other. Nobody else has any files anywhere, right? Okay.
Olivia Taylor to the office. Olivia Taylor.
Anyone confident enough to come show this? I mean, I'll do it. I don't care. I just want to know if somebody wants to come up.
I didn't calculate, but I can write my original equation.
If you want to, it's up to you. If you guys aren't interested, that's fine. Sure, yeah. I mean, I get paid to be up here. Not much, but a little bit. And some people go straight to the, I can go ahead and sum 20 plus 14. I don't mind if you do that. But I would be cautious about the distribution on the unknown line there. I would go ahead and write that out so you can see that.
I didn't really do anything.
So then we got to do 14 times 34.
I got it. 476.
And then you got 16 times 16.
256.
And then we can subtract the 256 from both sides. That's what, 220? Yeah. X is 13. Sorry, was it 13 perfect? 13.8. Any questions? Yeah.
I don't understand why the equation is.
So if we, and actually we could set up some stuff in GeoGebra and play with this. So if you're curious to see this happen, anytime I drag this point, it affects both legs. So if I drag this point like this way, and I instead connect here and here, well, this portion on the outside might potentially get shorter, but then my portion on the inside gets longer. If my portion here gets longer, then my portion there gets shorter. Like they're kind of doing not necessarily inverse of each other, but depending on what I do with my point. Now if I stretch my point way out here, then they might both just get longer. But either way, this is just taking the sum of the, I can't use words like segment because those are specific in my circle, but it's using the sum of this line, so the whole length times the portion, because that setup tells us where it is relative to our circle. Like there's this whole, I'll try to look up a better explanation that like kind of pieces through why. Like let me try to look up a breakdown that I can show you guys tomorrow. But for now, it's just kind of one of those, except that that's the rule that we've, like mathematicians for years have tried to disprove that just to say whether it's right or wrong, it's been proved that that works no matter what. I'll try to find a better explanation. I know it's kind of like, why does that work? It's just one of those cool relationships in math that it does. It's been found to work out perfect. Other questions that I can answer better? Sorry, that's not a very good answer. I'll get you a better answer. Yeah.
How many topics are in this unit?
In this unit, this is it. In chapter 8. Like, are you talking about this chapter?
Yeah.
This is the end of the chapter. So, that brings me now to like, when do we want to take our tests? So, we're done with chapter 8. I'm going to take at least a part of one more day to do questions and like help with any of the practices. So keep commenting on the Schoology page. I appreciate that so I can prep. So tomorrow we will probably just be doing questions over any of the chapter 8 stuff. But here's the deal. Next week I'm out Thursday and Friday. Because I have to go to a wedding in California.
Oh my
Cool.
god.
So, a friend of mine from home. From like childhood. And
Do you
like
remember
family
you?
friend. Huh?
Did you remember you?
He. But yeah.
He remembered.